Yeah. No.
Hello, everyone. Please sit down. I'm not going to make an introduction. Just if you need the microphone, please raise your hand, find me, and I'll bring you the microphones. Reminder for everyone, please use the microphone if you have anything to say for the people online.
Yeah.
Have a good afternoon.
Yeah, hello again. This is not going to be a tutorial. This is more like an overview talk of the things going on in my team in Oxford. I'll give a little bit more background information on how this is all situated together. Just about myself, for a long time I was actually at the University of Oxford in computer science as a professor. Then we built like a very big group there. There's some people in there. So Constantino should be here. Is he here? Not yet. Always late. So who else is there? I don't know. Anyway, there's a lot of people here, and a lot of them, they basically moved with me from Oxford University to the then Oxford Cambridge Quantum offices. So I'm chief scientist at Quantinuum, but I also have a team in Oxford. And I'm going to talk today about what we do there. And so in 2021, Cambridge Quantum was no more, and then became Quantinuum or something like that. And this was to be precise, if nobody has explained that. So what happened is, like Honeywell, the big American company Honeywell, had a bunch of people in a basement building quantum computers, and they didn't know it even, that this was happening. It was a very funny story. But yeah, they actually were very close to a quantum computer, and then these people realized that, and they say, hey, wait a minute. But then they didn't feel that building quantum computers really fitted in a traditional company like Honeywell. So they split off, and then they fused with Cambridge Quantum to become Quantinuum. So that's kind of what happened there. But I mean, So Honeywell and also IBM even, they're some of our main investors actually in the company. So we mainly get money from these other companies. Anyway, so that's the situation. And like I said, I've got a team in Oxford. So Richie should be somewhere there, Richie there. And who else is here from Oxford? Nobody. Me. Yeah, me. Thomas, where is Thomas? Thomas, where is he? Somewhere here. And he has a circle. Oh, there is Thomas. There's Thomas. Who? Ferdy. Yeah, Ferdy is here. He's not technically in Oxford, but I put him in Oxford because he does so much for us. Yeah, that's it. Okay. Right. And this is our logo. And I mean, you see, this is C, and the C stands for compositional, composing things. Like you saw this already this morning. A lot of what we do is about plugging things together and composing things. And this is, oh, sorry, I'm wrong. This is an I, and this stands for intelligence. So we're interested in compositional intelligence, like trying to understand intelligence, be it artificial or not artificial, in a compositional manner. And it also looks a little bit like a Q, you know, it looks a bit like a Q. That's because it's very quantum compositional intelligence, quantum-inspired compositional intelligence. And this was designed by Konstantinos, who's always late, who's supposed to give the next talk, but he's still not here. And then there was this really unfortunate accident that it actually looked like a skull. This was very, but yeah, I mean, we didn't have time to design a new one, so we stuck with it. Right. Okay, and this is our basement in our office. We got an office somewhere in Oxford, in Beaumont Street, and this is our basement. So we play some music there. Okay, language of quantum. So I'm going to go very far back in time. So this is John von Neumann, originally Hungarian, so not too far away from here. And von Neumann is known for inventing game theory, and so to some extent is the father of mathematical economics and things like that. And also the computer architecture like we use now, that's the von Neumann architecture. And von Neumann did a lot of other stuff. He did a lot of stuff. But one thing he did was he actually came up with the quantum mechanical formalism, the Hilbert space formalism, which we still use today. Soon not anymore, of course, like I explained this morning, but now we're still using Hilbert spaces, and they all go back to von Neumann. And von Neumann published his book, Mathematischen Grundlagen der Quantenmechanik, in 1932. 1932, he published his book. He sort of had done everything. He said, okay, now the formalism is ready. I'll publish a book. And then this is from 1935. This is from 1935. I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So 3 years after basically giving birth to the Hilbert space formalism, he denounced it. The father denounced the child. It doesn't happen much. No many people have the bravery for that. Now, I should say something. So von Neumann then went on in 1935 with Birkhoff to come up with some alternative to Hilbert space, which he called quantum logic. And I'm not going to go into that too much. I can tell you, you don't find it in any textbook for physics, so it's kind of a failure. You find it nowhere. You do find it in some psychology papers, but definitely not in physics. And the important thing to know about von Neumann quantum logic is that von Neumann felt that the most important thing about quantum mechanics was quantum measurement. And if we understand and conceptualize on quantum measurement, and maybe abstract, then we would build a better formalism than Hilbert space. That was von Neumann's opinion. So the focus was very much on quantum measurement as the key ingredient of quantum mechanics. So remember that. So this is Schrödinger, Austrian, not too far away. I mean, he's known for a cat and for an equation. But then another thing Schrödinger did, 1935, again 1935, is he said the following in some paper. So he's talking about composition of systems using the tensor product. Like you describe composite quantum systems using tensor product. And he said, I would not call that one, but rather the characteristic trait of quantum mechanics. So he thought very different than von Neumann. He didn't say measurement is not that important. What is important is what happens if you bring two systems together in quantum mechanics, and that's the characteristic trait of quantum mechanics. That's what Schrödinger said. So, I mean, most people historically, they followed von Neumann's line, because in his book von Neumann also did the first hidden variable no-go theorem. And so all of quantum foundations focused on measurement and measurement only, and it was all about measurement. And people were kind of ignoring Schrödinger for a long time. And until Samson Abramsky and myself, we put this paper out, Categorical Semantics of Quantum Protocols. And this was really like trying to build up quantum mechanics with composition as the only connective. So the only symbol you use is composition of systems. You don't use sums, you don't use all the other linear algebra stuff, and you see how far you can go. You see how far you can get, and you try to see which axioms you need to do something. And for example, in this paper, we basically just introduced these cups and these caps you saw this morning, and we started to derive things like teleportation. But it was all formulated in the language of category theory. There was no pictures, it was all category theory. And category theory, well, this kind of high entrance fee for a lot of people. So then this Roger Penrose, he lives in Oxford, he's in the Maths Institute. He also got a Nobel Prize for things like black holes. And you may know him from these Escher pictures, which he actually gave a lot of ideas to Escher for all these pictures. Then another thing Roger Penrose did in 1960 or something like that, when he was an undergraduate student and he had to learn relativity, he really didn't like this. He really didn't like this sort of tensor notation. He said, it's horrible, it's totally non-intuitive. And he started to substitute it with pictures. You see, here is an example of the identity wire, like we saw. And this is like, but mainly he was drawing these pictures. These things are not at all the same as our spiders. They just happen to be the same in notation. They're not spiders, they're just blobs. They're blobs, they're like our boxes. There's no more meaning to it than that. But anyway, he started to draw these pictures, and he realized that you could do all this tensor notation with these pictures too. And then I basically rewrote the paper with Samson, and I wrote the paper with a silly title, Kindergarten Quantum Mechanics, and I started to sort of, for the first time, do calculations with these diagrams like the teleportation I saw this morning. And then, okay, I'm not going to go through that, but then the idea is, of course, that you just do topological deformations of wires. And this is not something I said this morning, but if you take a box, and you wire the output into the input, and the input into the output, you're actually taking the transpose of a matrix. That's really what you're doing. So this is how diagrammatically represent the transpose. And you can also represent unitarity, and you can represent conjugates and adjoints, all these things just with wires and boxes. So that sort of stuff was in there. Okay, as 13 years later, there was the Dodo book. 5 years later, there was the book you now all have. And then, so, okay, the story succeeded. We had a quantum formalism entirely in pictures. Cool. So this is not what this talk is going to be about, but it's going to use it. So, okay, I'll skip that. What we're also going to do, you got this book now. We filmed the entire book, like lectures of the entire book, and they're going to be soon thrown on YouTube. No, I'm waiting for Ferdy. Is Ferdy here? No, Ferdy is not here. Okay, so he's in charge of like getting them out. But they're all done. So this is Stefano Goggioso, with whom I wrote the book. This is a moon, and you can see it can have different phases because it's got a dark side. And so there's lots of stuff. And there's also fun. We do also a little bit of stand-up comedy in these videos, just to keep it fun. Okay, so we've seen all this morning, so I can go. I'm just reminding you because we will need these things. So you got wires and boxes, you can compose them. You remember the cup wire, the cap wire, and then the fact that you got this yanking equation. This is like sliding a box, it's like taking the transpose. These are all things we're going to need for something else than physics later. Okay, teleportation, you've seen this all. Spider is all you need. The only thing I want to say now, which I didn't say this morning, is I want to give the philosophy of the spider. What is the philosophy of the spider? To understand the philosophy of the spider, you need to understand the philosophy of the wire. What is a wire? A wire is a thing that has two endpoints, right? A wire is a thing that has two endpoints. And what are the equations governing wires? If you take one wire and another wire and you glue them together, you get again a wire. Not very interesting. Like with wires, you can only create wires. And so the philosophy of the spider is basically that this is a wire with multiple ends. And then this equation, which I showed this morning, is basically, okay, if you got a multi-wire, and you got another multi-wire, because there's multiple possible outputs, not just two, then you get another multi-wire. So this equation is basically just a generalization of what wire is. So this spider fusion. I mean, I didn't say this morning, but it's kind of funny. Anyway, so we've seen all that. So the interpretation I give to this equation is you got these two spiders and they hate each other. And they both give each other a right hook. See, they both give each other a right hook. But they hit so hard that their leg flies away. And that's why you need two, because they both need to give a right hook. And that's why when you got two, they vanish. So that's the deep philosophy behind this equation. Okay. And then, like in the beginning, when we wrote this book, we actually wanted to sort of denote these phases with moon phases. And then Stefano started to draw them. And then just like me having to sign 100 books, he got a bit bored of it. So that's why actually that's the only mathematical thing we have in this book, is that we actually do right angles rather than phases of the moon. But you could have done phases of the moon in principle. You could have done phases of the moon. Anyway, so this is X calculus. As you've seen it, I've said that this is the people who proved the completeness of the X calculus, like that any equation you can derive using linear maps, you can actually derive now using this X calculus. This was for dimension 2. Okay, and this is like a review, H10. I mean, it's really very clear, very well structured. I mean, I don't think this is your average 10-year-old, but still. Okay, and so what is happening now? What? So what is happening now, currently, in collaboration with, this is us at Quantinuum, in collaboration with Oxford University a bit, and a little bit of IBM. What we are doing now, and that's why we wrote the book in the first place, and that's why we did the videos, is we're going to teach a bunch of teenagers quantum in pictures, like all these techniques with like proper lectures. So this will be the video lectures, and then some tutorial sessions in which they can try some exercises and things like that. And then we're going to take a bunch of Oxford University students, pretentious people, and we're going to make them take like a regular course, a regular quantum course with Hilbert space, and then we're going to let them both do the same exam. So, but of course, in one case, the questions are formulated in pictures. In another case, the questions are formulated in Hilbert space. And then we're going to see who wins. I mean, I've been telling this, the first time I talked about this experiment was 2009. And then I said, yeah, we're going to do it next year. Yeah, we're going to do it next year. But it is going to happen this summer, effectively. It's really happening. It's really happening now. Like recruiting is going to start next week and all that. So it is really happening this time. So that's going to be cool. So the point is just to prove that, yeah, I mean, it's just much better to use this picture than usual Hilbert space quantum mechanics. Okay, now the content of my talk is now really starting. So this is Jim Lambeck. Jim Lambeck is not a physicist. Jim Lambeck is a mathematician, was a mathematician. He was based in Montreal, in Canada, a professor of mathematics at McGill. And he also wrote the first paper which can be considered as proper mathematical linguistics. We're talking about linguistics now. So he wrote a paper, The Mathematics of Sentence Structure, and basically there he introduced, there had been attempts before, I should say that, but this was the first proper theory of something, a piece of algebra, that allows you to verify if a sentence is grammatically well-formed. So we're talking now about something completely different, right? Completely change of direction. So he came up with this theory to show that a sentence, I'm going to give a little illustration on how this works later. But anyway, so this was Jim Lambeck. He was in McGill. He was still alive in 2005 or something like that. So let's now go to Montreal, 2005. So we're in Montreal. And I just wrote this paper, Kindergarten Quantum Mechanics, and I was very proudly like explaining how you can do teleportation with pictures and all that. And then Jim was in the audience. He was sort of asleep. I mean, there was all very old category teachers in that. They were all asleep, but then suddenly they asked questions. It was very funny. So they were sort of in a state, in a superposition of conscious and unconscious. Huh? Yeah? And then Jim was there, and then he heard me saying that, and he said, Bob, this is grammar. I said, no, Jim, just go back dreaming. Like it's physics, Jim. No, Bob, this is grammar. And he was right. He was right. In a certain incarnation of his grammatical theories, a very particular one which is from 1999, which he published in 1999, and which he called pre-groups, as categorical structures. I didn't give you category definitions, but as categorical structures, these diagrams and his grammatical structures were exactly the same thing. And I'll illustrate later how this works. But so this is a remarkable coincidence from if you write Hilbert space and tensor product and linear maps in this language, then suddenly it looks exactly the same as a grammatical structure. And it's just a mathematical coincidence. I mean, I didn't take much notice of that at the time. I didn't take too much notice because I was starting the development of all these categorical quantum mechanics things. But then 3 years later, there were some colleagues in Oxford. So one of them was Mernouch Sadrzadeh. I know there's a few Persians here. Like Mernouch is Persian, is from Iran. Now is a professor at UCL in London. And she knew these grammar systems from Lambek, because Lambek had asked her to develop the theories for the specific case of Farsi. So she had developed this paper on a specific case of Farsi, pre-groups for Farsi. And so anyway, she knew that. And the way I'm going to try to explain how it works a little bit. So this is my phone. Ting, ting, ting. No, it's not mine. So basically what you got is you see these letters like S and N, and they represent what's called sort of basic grammatical types. They are grammatical types that of entities that mean something in their own right. So like a noun, that's a meaningful thing, it could be an answer to a question. Yeah? Just a noun on its own is a useful thing. A sentence is also a useful thing. And so these are undividable types. Now then you got other things like transitive verb. This transitive verb would have the type, an S, and you see I'm using like intuitively the idea of like inverses in a group. And a noun -1 and a noun -1, but the -1s are at different sides. What this means actually is a transitive verb wants a noun on the left and wants a noun on the right, the subject and the object. Yeah? He wants these two on the right, and by sticking the inverse there, he's actually asking for it. Give me a noun on the left, give me a noun on the right. And then so here is this transitive verb, these three things in the middle. And if you stick a noun on the left and you stick a noun on the right, these cancel out and you get a sentence. And that's the way you compute that noun, transitive verb, noun means sentence. And this is, of course, a very simple example, but this works for all of English and all of languages, actually. I mean, in languages, of course, there are differences. In some languages, you want to stick the subject and the object on one side of the transitive verb, and in another language on the other side of the transitive verb, and so on. Actually, for each permutation, there is a language where you use it. For each permutation of transitive verb, object, and subject, there is some language where you do it like that. So these type systems are a little bit different in each language, but the algebra is always the same. The algebra is always the same. So now what is important for what I'm going to say is that this little calculation which I did here, so I had a transitive verb in the middle, noun on the left, noun on the right, which cancel out. You can actually represent this diagrammatically. So this here is basically the canceling out. It's almost like an annihilation in Feynman diagram type stuff, you know. And these two cancel out, and then the sentence type goes too. Yeah? So we got a little diagram representing this calculation. And for each sentence, however complex, you can get such a diagram. You can get such a diagram. I mean, in the paper, let me go. In the paper, I think it's in Mernouch's pre-group paper. She actually, it's very interesting. She gives the these diagram structures for different languages. And then you see, for example, that for English and French, they're very similar. For Arabic and Hebrew, they're actually very similar. And then Persian is very funny because, for example, for English and French, the cups are very, very close to each other. They're small cups, like they're only words close connected to each other. In Farsi, there's like like words from one side of a sentence are connected to words on the other side of a sentence. So you can really recognize languages by the structures of these cups and caps. Okay, so that was my knowledge. There was also Steve Clark who was in Oxford. So Steve is now Quantinuum's head of AI. After he was in Oxford, he moved to Cambridge. After Cambridge, he moved to DeepMind. After DeepMind, he moved to our team in Quantinuum again. And he was doing something else. He was doing something that everybody now knows, representing meanings of words by vectors. That's what all the chat GPTs and all these things are doing, and all these large language models, they represent meanings by vectors. But this was 2006, 2007. There hadn't been any deep learning yet, and this was at the time just a purely academic discipline. This was not something that was taking place in industry very much. It was purely at universities. And so Steve was studying like how to represent meanings by vectors and what are the best ways to do that. But then if you produce these two together, okay, on the one hand, we've got grammatical structure, so how you compose words to make a meaningful whole and the rules to do that. There you got meanings of words. And then how can you combine these two? How can you combine grammar and meaning? For example, if I know the meanings of words in a sentence, can I come up with the meaning of a sentence as a vector? Is there some way I can combine this grammatical structure? Because the grammatical structure will have a role. That's really those are the rules of how words interact with each other. And if you've got the meaning of the words, can I basically come up with a theory for meanings of sentences, which you derive from the meanings of the words? And when Steve told about this problem, and to me, I say, oh, of course, I have a solution. Of course, I know how to do that. I mean, no, not really me, but Jim knew how to do that. Jim knew how to do that because Jim looked at these diagrams and said, these wires, they are like grammatical structure. What is flowing in the wires are vectors. Vectors, just like meanings of words and sentences. So it was an obvious conjecture that we could just use this categorical quantum formalism or diagrammatic quantum formalism to come up with a theory for how meanings of words combine to meanings of sentences. I mean, to me, it was obvious that it was going to work. To me, it was obvious that it was going to work. And we tried this, and it worked. It worked. So we published this paper, Mathematical Foundations for Compositional. This is because there is grammatical. Distributional, because you're working with these vectors, which at a time were interpreted as probabilities of meaning. And I'll tell you how it goes. So you remember, this for me is the algorithm. Basically what I'm doing is I take meanings of words. So the top are meanings of words. So this would be a vector representing Alice, a vector representing AIDS, a vector representing Bob. And then the bottom is the grammatical structure. This is this little diagram which we derived before from the calculation. And so intuitively what's happening here, so you compose them, and then the claim is whatever comes out here is the meaning of the sentence. Now, if you look at it a little bit, it's really like Bob is being teleported into Hades or just fed into Hades. Alice is being teleported into Hades. Hate is some sort of entangling linear map which actually makes them interact and puts them in the hatred relationship, so to say. And then whatever that is comes out here. So you got what comes out here is Alice and Bob in a hatred relationship. I mean, it's very intuitive, and of course we did a lot of experiments. This is an experimental science, so we did a lot of experiments with that, and it worked. It worked really well. Yeah. Oh, so a good question. Good question. So the question is, I'll repeat, how would Alice hates Bob be different from Bob hates Alice? Hate is not at all symmetric. Hate is not at all symmetric. It's like a very direct, you would see in the matrix of hatred that it goes in one direction. If this would be Mary's, then it's probably much more symmetric. Yeah, that's more symmetric. But so yeah, so this is some sort of quantum state, if you want, in here, and this will be not at all symmetric in these two inputs, not at all. So good question. Okay, and what you can do now, you see this is like a Dirac bracket on its side, a Dirac bracket on its side. I take this sentence, Alice hates Bob. I take another sentence, Alice does not like Bob. And then you can take it in a product, and then you can see how closely related these sentences are. And so you can start comparing different sentences, like how close are the meanings related. So that was a new thing, that was a useful new thing. So that was all cool. Now, then we worked a bit further. I'm not going to go too deep into it, but we were talking about spiders. And spiders also have a role in this theory. We use spiders to, for example, so this is she who hates Bob. So we use spiders to encode things like relative pronouns. Again, this is not something we just guessed. There is a logical reason to do that. I'm not going to go too deep into it. But the point is that such things like relative pronouns you can actually build from spiders, and then you do your experiments, and it works. There is some sort of conceptual justification to do that, but there is always like, with this sort of stuff, you do empirical experiments, and if it works, it's good. And this worked, so that's cool. Okay, so here is an interesting thing. So I was the only physicist of the team, of the three. I was the only physicist, and I told people, please don't mention quantum. When you write about this and you talk about this, don't mention quantum, because otherwise we're going to be branded as crackpots. Complete and utter crackpots. And then, like, immediately there were these headlines, like quantum linguistics, the quantum linguist, quantum mechanical words. So, okay, so this was around, what is this, 2013, 2010, 13, okay, so quite a while back, 10 years back. However, there was this man, Feynman, nature is classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. Okay, so you've heard about quantum chemistry, I guess, this week? Yeah, so chemicals, they're quantum. Chemical have quantum mechanical descriptions, so it's really hard to stick them on a classical computer. It's really hard to stick them on a classical computer. Now, this stuff, this theory, what am I doing? What happened? Oh, actually, this is funny. I'm going backward. This is the stuff which is going to come. Okay, good. I wanted to go there. Wrong direction. Yeah, so this sort of theory we had here, although I told them never mention quantum, but it was a theory of vectors and tensor products and linear maps and all that. Yeah, it's like a thing which is not easy to simulate on a classical computer. And we actually noticed that. Like, I mean, I didn't do much of the experiment. Steve and Mernus and others were doing these experiments. They worked very well, but they didn't scale very well because these tensors became very quickly huge. And they didn't really fit on classical machines. So, I mean, what basically happened at a time initially is like we just stopped doing it. We just stopped doing it. But then, I mean, I had this student, Will Zhang, who until recently was the head of quantum at Goldman Sachs, and he did a PhD with me. And then Will sort of suggested maybe we should actually take this idea seriously of like doing like language on a quantum computer, doing this natural language processing, distributional meaning natural language model on a quantum computer. And so the first thing we did is like, we basically looked at what are the typical things people in natural language processing would want to do with meanings of sentences. And this is stuff like comparing them, maybe classifying them, seeing whether a headline is about sports or Romans or politics or whatever, these sort of tasks. And then we discovered that for all the sort of typical tasks, you would get a Groover-like speedup. So it's not just that it wants to live on a quantum computer because of the size issues, like because the size is so big of these things. You also get algorithmic advantage. I mean, when was this? 2016. I mean, Will sort of took it seriously, but I still thought it was a joke. Honestly, I thought it was a joke. I didn't take it seriously. But then Elias Kahn, around 2019, I was in a pub with him and I was sort of joking about that we had done that stuff. We had sort of looked at this natural language stuff from a quantum glass, a quantum computing glass. And then he said, hey, Bob, you need to take this seriously. Here is some money. Do it. So, okay. So I built initially a team like Konstantinos, who's still not here. And Alexis and Giovanni. And we actually were able to do question answering on a quantum computer. So we used a real quantum computer. We trained it with something. We did some question answering, and it worked. I mean, I was astonished that you could do anything like that, because typically NLP and all that stuff is considered as really heavy on data. I mean, the amount of training data these GPTs use is just ridiculous. It's just ridiculous. And we did all this with good results with very little data. We could do this with very little data because we had this linguistic structure working for us. The ways these words interacted through this grammatical structure was helping us a lot and allowed us to do things with very little data and in an interpretable manner, by the way, in an interpretable manner, because we understood what was going on. Okay, so then we started to do sort of bigger experiments. This worked. And then, basically, we took all the software we developed for that, made it very nice, made it very clean, made it very readable. Richie works on everything. Sleep. We made it very readable, very user-friendly, and we threw it at the world. And and you can use it now. Now, you can go there. What you should look for is Lambic. You kind of imagine where this name came from. Lambic with a Q at the end. So this is our software. You can just download it, and it connects. You can type in sentences and stuff, and it connects directly to a quantum computer, and so you can do that stuff. You can do question answering on a quantum computer this evening if you want. So it's all available. Yeah.
If I understand well, this kind of approach you're mentioning, isn't it closer to, let's say, old school NLP in the sense of expert systems rather than machine learning type of NLP, which are based on statistical patterns nowadays? So
it's a very good question. So the structures we use here are they're completely different than the old propositional structures they used in AI. They are very compatible with the machine learning techniques you use. They are sort of more like an umbrella rather than a skeleton. So in these wires, we use training. So I'll explain. We train in the usual way the data on a quantum computer in something that looks like a neural network, but it's interpretable. So it's a subtle difference, and we actually need to work harder to actually explain this clearly. But I'll show this later. You'll see this. Okay, after we started doing this, like people at IBM started to. So DiscoCat, that's the name of the thing. It's a horrible name, but that's the people at IBM start to use that. And then these people start to use some generation, use the same thing for some generation. Also, people at IBM, they wrote, actually, if you want to read about this, they wrote a very nice blog, like a blog post about all the stuff I've been talking about now, yeah, this quantum natural language stuff. Okay, so then we want to do something different, but without much work. So basically what we did next was we took out the linguistic grammar out of the system, and we put in instead a musical grammar. These are things which exist. You can write grammars for music, and so without much effort, we got actually a new piece of software which is called Quanthoven. So Quanthoven is pretty much the same, but for music instead of for language. And then without much effort, we sort of generated some silly pieces of music. And then suddenly, Bob Cigarbos, one of our songs, like from Ludovico Quanthoven, became #1 in some classical charts. Again, you can do this yourself. The software is available. You can go to GitHub, get Quanthoven, and play around with it. Okay, so what's happening inside Lambic? That's the answer to the question, more or less. So you got this diagram. You shouldn't think of this as a logical system. It's not sort of these are not symbols. This is not a logical symbol. This is not a logical symbol. This is not a logical symbol. This is a trained state, something like you do in modern machine learning. This is a trained state, and we're now going to start deforming this. I'm introducing some spiders to actually reduce the size a bit. That's all stuff which is empirically justified. And now I'm formulating it like this. So you got Alice, and now you see better, like Hayes is sort of entangling Alice and Bob, almost like a circuit. Now I turn this, now I unspidered, you see? I pulled out spiders like we did this morning, and now you see C0 gates appearing. Quantum computers don't have much qubits, so we reduce the size a bit using all the sort of deformations we saw this morning. And now we need to parameterize. Now we parameterize these boxes. So that's the big difference. They now get parameterized like a neural network, and you end up with something this. So you can think of this like a neural network, but these are phases which we will train. These are the phases which we will train. Now this represents the transitive verb, this represents Alice, this represents Bob, and so we get this network and we're going to train it. We stick it on the quantum computer and we train it on the quantum computer. Why do we do that? Because you can't stick data on a quantum computer efficiently. So the way to do it is basically to train the circuit, and that's what we are doing here. So in a way, this is a neural network, but we know that this is like the subject, we know that this is the object, we know that the object is connected to the transitive verb here, and the subject is also connected to the transitive verb here. So the linguistic structure is in this network, so to say. It's present in there.
Sorry.
Yeah.
What is the data and what is the cost?
Oh. Which one did we use?
So it depends on what problem you're solving. So you convert each sentence into a quantum circuit, and you would learn the weights of your model based on the objective function. And you would do that based on the data, the labels, and you would pick it appropriately. It's supervised learning. So the sentence structure, the syntax tells you the shape of the circuit, and each word would have its own set of parameters. So those will be the embeddings for the words. It depends on your task. It could be classification. It could be, it could be sentiment analysis. Yeah. Sorry? For example, you could do that. For example, yeah. Yeah. It's the dapper quantum. Yeah. Supervised learning is, yeah.
Yeah. So yeah, I mean here the diagram. So this kind of we just use like it's kind of a hybrid thing, because what you're training are actually the classical settings of your quantum circuit. So it's sort of half quantum, half classical in a way. It's a hybrid thing. It's the same as the chemists do. The same as the chemists do, pretty much. Okay. Now what you see here is a sentence but represented as a quantum circuit. Forget about the quantum, sentence represented as a circuit. Usually when we speak, words are on a line. Words are on a line, right? So here, words form a circuit. And I mean, this was for the reason that we wanted to stick it on a quantum computer, so it needed to be in circuit form. But I mean, in parallel with these developments, all the previous stuff we had, all the previous theory we had, and all these grammatical theories from the past, they were all about when is a sentence well correctly formed. So it was all about sentences. So far we only had an algorithm to give meaning of sentences given meaning of words. Now, sentences are not the most interesting linguistic entities. Texts are much more interesting. I mean, you don't buy a sentence in a shop, you buy a book in a shop. Sentences are not very informative on their own. And so I'd been thinking how to generalize this theory to text, and so we came up with this thing called text circuits. I started this first in this paper, The Mathematics of Text Structure. And basically, at some point, we had this representation, do you remember? Rather than, and so basically, we got here an Alice wire, and we got a Bob wire, and they get entangled by heights. That's sort of the idea. You got an Alice wire, a Bob wire, they get entangled by heights. But nothing stops you from doing this. Introducing a third entity, beer, and then also entangle Bob with beer through likes. And so you can go on. You can go on and you can basically form something which is closer than a text. And then what is beautiful about this, and this, so far, Konstantinos is still not here. No. He has 17 minutes. Okay, so because he's working on this. So basically, you got a circuit now. And so a text is basically a circuit where you got a whole bunch of agents. This could be the actors in your story if you want. And then a bunch of relationships that happen, like actions that happen between the agents. But ultimately, this is basically like a quantum evolution. This is very much like a circuit you would do if you want to simulate the chemicals. It's the same thing. So a text, so basically reading out or executing a text is pretty much the same as executing the evaluation of a quantum system. And so we're now starting to work, but our expectation is that the sort of speed-ups we can get here, the advantage we can get here with these pneumatics is going to be much more than the sort of Groover-like stuff. So personally, we are not a quantum machine learning group per se. We use quantum machine learning, but in a way we're closer to the people who do simulation, the chemists, with this new theory. It's actually much closer because we got this quantum theory of language, of interaction, and it basically wants to live on a quantum computer, and we're expecting these circuits to be really, really hard. Really, I'm going to use the term tensor network because people like that. These are really hard tensor networks to simulate, very hard tensor networks to simulate. So that's the stuff we're starting to do now, and we're hoping this year to get some really nice results with that, demonstrating how hard they are and stuff. This is sort of a special occasion. There's people from many different countries here. How many different nationalities are here? Does anybody know? 24. 24. So we got many different nationalities, many different languages. And what we start, so basically me, Vincent, and Jono, we wanted to develop this theory of text circuits very properly, understand very deeply mathematical what these circuits for text are. So what do they teach us? How are they different from just language on a line? I'm not going to go into great detail, but basically what we did is, this is also a grammar. It looks very different from the Lambe grammar. This is more like a Chomsky-style generative grammar. This is more like a Chomsky-style generative grammar. So you got these little bits, and they generate like pieces of text, and then you can build a tree, and then you get a text. And here is some pronoun resolution going on. So we created this grammar specifically to get a very nice mathematical statement. We wanted to know what is the structure that feeds into building a circuit for text. So we had this stuff, and now I'm going to do a linear. So this is basically just a sentence on a line, like we usually speak, together with its grammatical structure and some other stuff. Now we're going to start deforming this. So we throw these links. I mean, it's not important that you understand what's going on, but this is a mathematical algorithm that we have, which turns every text into a circuit like this. So every text becomes a circuit like this. And you see, you can go back to the sentence. Sober Alice, who sees drunk Bob clumsily dance, laughs at him. And here you see Alice, sober. She sees Bob dance clumsily, is drunk, Alice laughs at Bob. So all the data is there. All the data of the sentence is there. Now you can ask yourself, is the sentence faithfully represented there? Maybe, maybe not. Okay, and then you can ask another few questions. And then we came to two very remarkable conclusions. First of all, these circuits are the same in every language. There's no differences. So suddenly all languages become the same, which is quite a remarkable thing. I mean, I really love you, je t'aime vraiment. They give the same circuit, but you can do the same for really complicated sentences, and you get the same in every language. So this is this is inter-language independent representation of meaning, which is pretty cool. I mean, I was shocked when I saw it. And more also, so here you see sober Alice, who sees drunk Bob clumsily dance, laughs at him. Alice sees Bob dance clumsily. Alice laughs at Bob. Bob is drunk, Alice is sober. They give the same circuit. So the style, your style, how you write things, long sentences, short sentences, punctuation, relative pronouns, all vanishes. There's no punctuation anymore here. It's all gone. There's no relative pronouns anymore here. It's all gone. So it's also an inter-language independent representation of language. It's a lot more economical than usual language. Now, what is the philosophy here? Konstantinos is still not here. There he is. Oh, he's here now. He's here now. And he wears his own T-shirt, you see. I mean, me too. He wears his own T-shirt. So the story here, what is the moral here? The story is, we as humans have no problem thinking about things in parallel. If you play music, that's why I showed this music slide, you are aware of everything every other musician is playing, and you're immediately anticipating what they're doing. So we are perfectly able to perceive things in parallel, several different things in parallel. Not too much, but we can deal with it easily. And oh, there's the other Alex with KS. So for the first time I met another Alex. This is my Alex with KS, and now there's another Alex with KS. Okay. So yeah, that's Ross Duncan. He's the head of software. He's the builder of Ticket. Anyway, so we can think in parallel. Now, unfortunately, this device I'm speaking with here is pretty bad in saying words in parallel, side by side. The only thing it can do is saying one word after another. That's all we can do. We can't. So for me, this is how language wants to be represented fundamentally. But we as humans, we can't speak like that. We can't say this. We can't say that thing. So what do you have to do? You have to work backward. You have to work backward. You have to take this thing and try to put it in a line one way or another. So that's the opposite algorithm. Huh? So you start here, and then you start to do things and all kind of acrobacy to get that thing on a line. And there's many different decisions you can make there. Like where are you going to put your subject? Where are you going to put your object relative to your transitive verb? All this, and then typically, if you don't use punctuation, you get something super ambiguous, something that you can't really interpret. So then you need to introduce commas and stuff like that, just to basically get an unambiguous representation of that circuit on the line. So in every language, people introduce different bureaucracies. You can use different styles to do the same thing. You use relative pronouns, you don't use relative pronouns, things like that. But so you get something that wants to be that circuit, but unfortunately can't. So, I mean, if you go, for example, to the Dodo book, for those who have done that, we do a long discussion there, and we compare the diagrams to symbolic mathematics. And then the symbolic mathematics is really complicated for a given diagram, because again, you have to make many choices, because you're sticking something that wants to live in 2 dimensions on 1 dimension. And you can't do this in a unique way, and lots of ambiguities arise. For example, the definition, I mean, somebody mentioned the definition of symmetric monoidal category. No? If you look at the definition, you find this in a textbook on category theory, McLean, on page 300. And you pretty much need all the definitions of the book, like natural transformation, blah, 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 to properly define this symbolically. Super complicated definition, and basically what you're defining is boxes and wires. Yeah?
But isn't it your framework at the end I mean, by just is not pejorative, but a very efficient compression algorithm? Because if you lose the style, meaning that you extract from a text written by a 10-year-old kid describing the day, and you ask the same thing to, let's say, James Joyce, who spent many years in Trieste, the same, maybe the fundamental meaning that you're grasping, the final circuit that you get is the same, but it's very clear to anyone that it's a very different thing that you read at the end. So isn't it just compression from the information theoretic perspective?
I mean, you throw away stuff that means nothing. So to that extent, it's probably compression. You throw stuff like the bureaucratic choices. Now, the style differences, of course, the commas and all these things, these bureaucratic things we need to introduce in a line, you can use them for art. That's what you're saying. You can use them to make poetry, and rhyming, and then you can do lots of funny things when you put on a line, which you can't do here. I completely agree. But for, this I would call like that's the machine language. That's sort of the language of a machine, which can actually speak in these two dimensions, like a computer. We humans, we do other stuff with it. I agree with you. Now, what you would now thinking, for example, translation. What you would do is, for example, you could train. So this is you could train something that turns the circuit into a text of a certain style. Of course, you could train that given enough data, and so you can actually basically have a style changing stuff like that using this intermediate. It's an intermediate form.
Yeah. But so my point is the size of this circuit that you get here connected in some way to some Shannon entropy that you can associate to your text, or
I don't know.
like
Honestly,
a fundamental level of compression of the information content?
So I must say we haven't really looked much at the quantitative characterization of how small it becomes. But I've got some examples. Let me show. Like, okay. So for example, here you got, this is just factual text, the pawn next to a king that a knight can capture. So we developed some linguistic theory of space, and this would be the usual sentence which characterizes this thing in the context of this chessboard. This would be the normal representation. This is the circuit. So there's a huge, we don't know quantitatively how much this is. We don't know, I should say that. But it is an incredible compression, like you say. It's an incredible compression. I mean, I've got a more extreme example here, I think. The ostrich next to the tree that a cheetah next to the grass can capture in human language, and here a circuit. So it's true what you say. You see it here with your own eyes. It's a huge compression.
Maybe it could be interesting to try to look at the size of this circuit and actually compare that to fundamental lower bounds given by classical Shannon entropies.
Yeah, exactly. Good idea. So what we've been doing, and Richie has been working on that. We've now got a pipeline where for arbitrary text we spit out the circuits, and we actually want to. The thing more important for us to see the quantum advantage of executing this on a quantum machine as compared to how you would do it on a classical machine. That's that sort of thing, because we're a quantum computing company. That's the thing we are shooting for, and Konstantinos should be doing that, and Konstantinos is still not here. I think, yeah. I mean, I think it's not just a compression. I actually think, and that's the same discussion, that these circuits are also closer to how we as humans perceive the meaning of language. Like, for example, here I've got an example. This is a movie, Once Upon a Time in the West, and you can really think of this circuit that you see here, like this happens, and this happens, and this happens, and this happens, as like a screenplay of a movie. So these circuits for me are much more, when I tell the sentence, like something like before, let's go to this one. Oh, sorry. Let's go to this one. The ostrich next to the tree that the cheetah next to a grass can capture. I mean, if somebody tells a sentence like that, maybe not that's complicated, then you imagine an ostrich and you imagine the animal and you imagine a chase, right? You say the tiger is changing the zebra. Well, you imagine a tiger, I mean, I do at least. I imagine a tiger chasing a zebra. So to some extent, for me, this algorithm is also how texts translate in how we imagine things. So it's more a cognitive, it's closer to our cognition, I would say, than the text structure itself. But again, more experiments need to be done with that. But that's my understanding, that these things are much closer to how we actually think. So I think, yeah, so basically what we're doing in the team is we're actually trying to use these structures to come up with some sort of models of thinking, both human and artificial. That's kind of what we're doing in the team. In Oxford, I gave some examples, so that's kind of what we're doing. Oh yeah, that thing looks also, yeah, that's now the skull is actually used to positive use. Okay, I stop here. Konstantinos is still not here? No. Oh, he's sitting outside. Okay, thank you.
We'll take some questions. We have time, right? Yeah, we've got a few minutes.
Thank you so much for the talk. I was just wondering, does it also incorporate the conjunctions part? For example, if I want to say Alice hates Bob, but Bob loves Alice. So how would I say the word using these circuits? Like, how would I represent it in the circuit form? I want to represent the word but. Like, same is the case with other conjunctions as well.
So what? I mean,
You can swap you can permute the wires. So
yeah.
you can permute the order of Alice and Bob after the first box, and then you can. You just gave an example where like the subject and then the object, and then now the object becomes the subject, right? That's what you're saying. Yeah. But that kind of gets abstracted away from the. That in this model you kind of don't have, you have these connected words are removed from the model. So there are kind of intentional things that we abstract away that we consider, like we're not handling this particular part.
So when are we going to put the pipeline out? So we have a tool. You just type in whatever, like the example you give, and it gives you the circuit. And we basically use a parser. So we use a traditional CCG parser, and then mainly Richie and some others, they've come up with then the algorithm. How you actually, from your CCG parse, you have to do extra stuff because this is not just a CCG parse. You have to do extra stuff, and then you always get a circuit. Of course, like with every parser, there can be some ambiguity in your given data. And so it's a probabilistic process, but most of the time you get this out. And for all these words, it gives the right type, and then the type turns into the circuit.
We actually have a version of this tool sitting on our Discord. So if you go into the QNLP Discord and you message Jimbot, so it's like a robotic version of Jim Lambeck, you can like type these texts at him and he'll reply with the circuit diagram. So we have like a version of, like the working version of our converter sitting as a bot on the Discord. So you can play around with it afterwards.
So go join the Discord, enter on the Jimbot chat, and you'll have the answer to what your bot actually looks like in the sentence you were asking. Any further questions?
Yeah, thanks for the great talk. I was just wondering, how does the representation handle grammatical errors? Will the representation break?
In principle, yes. I mean, there are tools around to actually deal with ungrammatical sentences and try to make the best of it. So you can use them if you want to. For most of the things we developed, we kind of assume. So what does Richie? What does Lambeck do with an ungrammatical sentence?
So this is a grammatical parser, right? So given a sentence, it will output a diagram, a parse tree, and also the associated probability, or like how confident it is. So if it's below a threshold, it will just say like this is non-grammatical, but it will try because some words it may not have seen, and it will decrease the confidence. Yeah, it's a parser.
Hi, thank you. So what would you say, or what would you expect the main advantage of QNLP to be compared to classical NLP? Like you mentioned the requirement for training data. You said because there's this inbuilt linguistic structure already there, you need less data. And is there anything else?
Yeah, well, the number one thing would be interpretability. So you get interpretability, which is an important thing, and we're actually working to get it even more it's a very important thing. I mean, I can't really. I was talking to a very big firm, and they basically told me that they couldn't use. They were not allowed to use because of regulations, international regulations. That was not interpretable. And with what's been happening in the last few weeks, I think this is going to become even more extreme. So you got interpretability, then basically the fact that these are really hard tensor networks and you can't really stick on a classical machine very easily. And then we're expecting also huge algorithmic advantages because of this difficulty of a tensor network. Speed up, like for quantum chemistry, same thing. And I don't know, like, a lot of research needs to be done, and we still don't know where the large language models are going. There are things which they clearly fail at, where we expect this to be much better at. Because, again, and it's connected to the interpretability.
So you have spent quite some time in explaining this compression, what I understand as a kind of compression or coding process into circuits. But at the end, this technology, in NLP, what we're looking for a lot are generative models. So is this at the end a generative model?
So the beauty of this one, is whatever you stick together, it's always correct. Like with grammatical structures, you have to be careful. Like it was mentioned, non-grammaticality. Here, everything you stick together, at least is structurally valid. So you can just, it's like with Legos. Whatever you build is okay. With the old syntactic models, like this one, it's very easy to do something wrong.
But in a generative model, there is no notion of correctness or not. It's just you have an input and then you generate new content.
Sure. So, but I mean, if you would want to, I'm just comparing to this one. If you would want to generate content here, this would be complicated. If you want to do it like us, like fully structurally, this would be complicated. And with the circuits, there would be no complication whatsoever. It's always correct. So it's a bit different. It's a bit different.
So it's not a generative model?
Not in that, I mean, I'm using generative like in, can you generate text?
Yes.
Yes, and then, so we can generate text in the same, like we generated music. We've done the music generation before. Now you can do text generation with the new, this was all with Lambic, by the way, the music generation. Now with these text circuits, it's much easier for us to generate because there are no constraints anymore. Before there were many constraints. But it's very different from, it's generative in the semantic meaning of the word generative. Not generative in the exact precise meaning you would use with a large language model.
So what you've seen so far is quite like kind of discriminative, like kind of classifying models. So it's not quite generative, but there is some work that we're working on that will make it more generative, like language models sort of stuff. So talk to Constantinos afterwards.
Yeah,
we can
yeah, we're starting a translation project now, so then you have to be generative.
But you're
in
right,
their sense.
It's kind of more classification than what you see, because you kind of measure and you kind of see which class it belongs in the most. So the setup we have here is more classification than generation. Yeah.
We'll take one last question from the gentleman over there.
Your boss don't like to hear it, but do we need quantum computers at all? Or, I mean, this is independent from quantum. I can do it on paper.
I mean, we expect this to be really hard in the first place on a quantum computer to simulate such a circuit. And then there is the expected algorithmic advantages. So, but at the same time, we have like a classical implementation of these circuits, and we're testing them, and we're seeing. So what we especially see, that's also for Jean, what we especially see in the experiments we've been doing with this is the incredible reduction in the need for data if we use these sort of circuits rather than neural networks. The data reduction is enormous. Again, we haven't quantified it exactly, but are you involved in the Bobby stuff? No. Are you? Yeah.
Okay, we'll give you a break. I suggest you come back in 10 minutes unless someone has a strict schedule. We'll do a 10 minutes break and we'll be back. Thank you.